What follows is an explanation of my custom game engine built with C++ and OpenGL. In the last video, I described how the GUI root manages the GUI controls. In today's video, I will explain the class that helps to encapsulate specific sections of the front end, the GUI Screen base class. I'll also explain the class that manages the GUI root and the GUI screens, the front-end manager. As you can see from this diagram, the game class manages the front-end manager, which in turn manages the GUI root and the GUI screens. The GUI root manages the GUI controls. I have not mentioned the game class before, so I will do so briefly now. The game class is a base class that holds an instance of all the managers that the game uses. It has the base functionality that is required for all games made with this engine, such as altering graphical settings and freeing level memory. I derive a game-specific class from it that contains individual functionality for a particular game. The GUI Screen class is an abstract base class. Every class that derives from it will have to override the initialize and update functions. It holds a string to represent the file it will open, a sound effect instance to provide audio feedback when the user selects an option, an enumeration identifier of the screen type, and a GUI root array index specifying whether the screen belongs to the main view or the one used for the level editor. The constructor sets the default and calls the initialize function of the selection sound effect to set the sound I want played. I put the function here rather than in the base initialize function, so I wouldn't have to remember to add it in every derived class. PlaySelectFX is self-explanatory. Free memory deletes the children of the GUI root that are referenced through the file name. Let's look at a concrete example of this class. The main menu class inherits from the GUI Screen class. It holds a texture animation for the portal used as a highlighter. The initialize function sets the enumeration identifier. The file name returned by the readDataReturn path function is the full path name, which includes the current language folder. In the main menu text file, we see the root defined first. It needs to be defined first so that the subsequently defined controls can have a parent. The rectangle defines its position to be 0 on X and Y, meaning that it is located at the center of the viewport. The vertical flow boolean is set to true, so that implies the options will be vertically arranged and will utilize the vertical arrow keys and the vertical sections of the D-pad to iterate through the options. The next widget to be defined is the menu background icon. It becomes a child of the GUI root when it is instanced in code. Since its position is 0, 0 and its size is 1, 1, it is located at the center of the GUI root and is of maximal size in proportion to it. Enforce original proportion is false, so the background will be resized in direct proportion to the GUI root when the screen resolution is changed. The highlighter is next, so it will be drawn on top of the background but behind the buttons that are defined after it. The first button is the Stage Select button. Its model is invisible because we only want its text to be shown. We set the mouse over sound effect, but leave the mouse release blank. The other buttons are similar. They are just offset at different values on the Y position ordinate. At the end of the file, we define the cursor. It, being defined last, means it will be drawn over all the previous controls. Any control defined as the cursor will be updated to the mouse's position. We return to the main menu class. The Stage Select button is set as the active control, making it invocable by default. We get a pointer to the highlighter to retrieve a pointer to its model's vertex buffer, so we can initialize the portal animation. The vertex buffer was described in my texture animation video. The update function checks if the Fade Manager's black screen is fully transparent before allowing the subsequent functionality to be invoked. The highlighter's portal animation is updated. We check whether any of the buttons have been selected, and if so, we play the selection sound effect and create the corresponding GUI screen. The front-end manager manages the GUI screens and the GUI routes. Its module is placed within the game-specific code folder rather than the engine code folder because it utilizes game-specific GUI screen classes. It uses an enumeration to classify each type of screen it can instantiate. The manager inherits from the Interface Manager class, which gives it a set of virtual functions common to most of my managers. It is also a singleton. The GUI screen pointer is used to instantiate the requested screen. The screen stack array allows us to record the screen IDs of the screens that were previously instantiated, so they can be reinstantiated when the go back message has been received, which means the escape key or B button of the gamepad has been released. The screen index is used to specify the subscript position in the screen stack array. The X and Y translation positions are used for helping to convert the mouse position from screen space to world space. The collision position is used for storing the final result of the mouse conversion to the world position transformation. The message is used for representing an input device's action. This message is then passed down from the GUI root to the rest of the tree until it can be processed or ignored. The constructor sets the screen index to -1. It will be incremented upon its first use to represent the first subscript of the array. The message is also set to null as default. The initialize function instantiates the GUI roots. I turn off input processing for the level editor because I only need the main view's input enabled upon startup. We cache some GUI screens so we can access them with reduced latency. Invoke screen ensures that we are not trying to re-invoke the current screen, and if we are not, we delete the current screen. Delete screen frees the memory of the GUI screen and clears the model cache to ensure we're not referencing a deleted model. It would be better if I just ensured that the GUI screen's current model was not referenced. So, using this function is too blunt of a tool. Back in the Invoke Screen function, we instantiate a screen based on the screen enumeration value. PushStack assigns the current array index to the newly invoked screen's ID. PopStack deletes the current screen, sets its array index as invalid, then invokes the previous screen. Resize GUI calls resize all, which calls scale and position for all the GUI root's children. The previous video describes this function. Update calls the update functions of the current GUI screen and the GUI roots. Calculate viewpoints uses the current game state to determine whether to subtract the level editor's viewport segment from the main view. It is only needed during gameplay if the level editor mode is enabled. Process input checks for whether an input action has been selected. An input action is set when the corresponding input key, control, or button is pressed or released. Due to a lack of demand, I will forego an explanation of the input system, at least for the time being. The go back action is a special case. During gameplay, there are multiple screens that can be invoked one after the other when the game is paused. For example, the pause screen can lead to the game options screen. So, I check that the screen index is 0. This indicates that we are at the bottom of the screen stack. Deduction implies that we must be in the pause screen, so we can unpause the game in this circumstance. We then call PopStack to remove the pause screen. At the end of the function, we translate the mouse cursor's position from screen space to world space. This conversion has been explained in the previous video. We then call the process message function of the current GUI root. Free memory deletes the current GUI screen and frees the GUI root memory. So, did you get all that? You want me to explain it again? No? Well, good luck.